So we're starting our conference. We're celebrating the 65th anniversary of Dr. Zach, who did very beautiful and international mathematical studies, and which also influenced many people in this room, I guess, including organizers of the conference, participants of the conference. And I think we'll see various signs of this influence during the talks in this week. And our first speaker is Peskine, who will speak about projections of intersection of quadrics from linear spaces.
Well, thank you very much. In fact, I'd like to thank the organizers 3 times. It takes time. So, the first time, I'd like to thank them for organizing, for celebrating Fyodor's birthday. And I'm very pleased that we celebrate Fyodor Zach here. I mean, I was one of those who in the 80s were stunned by the classification, the great classification theorem of Fyodor, which indeed changed in many ways the life of projective geometry, of classical projective geometry for many years to come. The influence was really enormous, and all around the world, I think people are working without knowing very clearly, influenced by this impressive work of Fyodor and everything he has developed around it. So I should say that it's very important for many of us to celebrate the 65th birthday. I already celebrated your 60th birthday, Victoria, organized by Quack. He's not here. I saw his name, but he's not come.
He's on the way.
So I'm very happy. I hope also to be there for your 70th birthday, and maybe 75, etc. So that was the first reason for which I wanted to thank the organizers. Second reason was to ask me to come and to talk. And because, in fact, after I met Fyodor in '91 by accident in Bergen. He had been invited there by Holmer, and I was invited there by, as we say nowadays, my descendants, friends and descendants, Guy Elixbury and Stanley Strammer. And we met there and we began discussing, and we've been discussing since that regularly. And we've been discussing about projective geometry. I asked him to come to Paris, and at some time we were in an INTAS project together. Many of you do not know what was an INTAS project. An INTAS project was a Russian-European project in the 90s, putting some money to help Russian mathematicians to decide to stay in Russia. And so it was a very good project that worked very well. We had several meetings around that project. When Skype came in, Fyodor and we used to talk regularly about projective geometry by Skype. For both of us, it was very important because Fyodor has another activity, as many of you know. He's an economist also, for some reason. So he is an economist and a mathematician, and I was a politician in mathematics for many years. So it was very good for us to discuss projective geometry in an amusing way. We disagree all the time. We shout at each other all the time. In fact, I always ask questions to Theodore about topology and geometry, and he asked about, he says regularly, this is algebra, this is for you. And I always remind him that once he told me that the Russian writer wrote that among Salieri and Mozart, Salieri was the algebraist, so I couldn't solve much in algebra, but still we go on discussing and disagreeing, and it's a great pleasure. I have a lot of pleasure disagreeing with Theodore. I wouldn't exchange that for agreeing with anybody. In fact, he comes regularly to my house in France when it's possible, and my wife said, I'm very pleased that he's coming, but try not to shout at each other too much. And that's how we've been doing for many years, and I hope we'll do that for many years to come. So I'm very happy, very pleased to be here to salute Theodore for this occasion. That was the second reason. And the third reason I want to ask the organizer is that they asked me to talk first in order that I could tell you what I just told you. So that's the third reason. And perhaps also it's good to talk first because then you're done with your talk and you can listen to the other speaker with great pleasure all along the conference, and that's what I intend to do. So I will be in fact, quite elementary. I will start with what I want to study to describe to you is how, if you take x in intersection, a complete intersection of k+1 quadrics in Pn, okay, and if you assume that there is a linear space contained delta, linear space contained of dimension k, of course, all this is complex geometry. You assume that there is a linear space delta of dimension k contained in this complete intersection, then it's very, if the intersection is general enough, it's very easy to see that the projection from Pn to Pn minus k minus 1 with center delta defines a birational correspondence between x and Pn minus k minus 1. And this is, I would like to talk about this birational correspondence. And in order to understand that, to understand the principle, it's enough to look at a couple of examples. The first example, the most easiest, is to take one point, x, in a quadratic, in P3. Okay? So if you project the quadratic, you look at the projection from P3 to P2 with center x, and you get, you look at this projection, and you know as well as me that there are two lines in Q through X, that is the two lines that project in 2 points, which I in P2, and in fact you have the graph of the projection is very simply the blow up of P2 in the 2 points, image of the two lines of Q passing through the center of projection. Okay, this is a very simple figure. You can go a little deeper in that and study and try to understand from that construction the so-called Fano variety of lines of Q. Of course, we all know what are the lines in Q without knowing what's a Fano variety, and that is my case. So we shouldn't worry too much about that. But nevertheless, if we want to describe all the lines in Q, they form a variety. In fact, they form a non-connected variety consisting of two conics in the Grassmann variety of P3. So what we have is that we have a Fano variety, such a projection defined, in fact, a projection from G1 P3 to G1 P2 The projection here, we take this is the projection we center. Here we chose a point. The point defines the alpha plane in G1, P3, the linear space. This is, of course, I should write in P. This is in the P5, okay, and this is P2 dual. So we have this projection here. This is the restriction of this projection, okay, and we see immediately that here we have, I mean, the standard variety of our quadric. This is the two conic parameterizing the two disjoint conic parameterizing the line in our quadric project to two lines here. Okay, but what is the image of the two disjoint conic? It's two lines which intersect in P2 dual. Okay, so what we see is that the Fano variety of Q is in fact the normalization of the one sequence line with the frame in P2 to the fundamental locus in P2. All that is a lot of work to say something trivial. Okay. Here we have in P2 we have the fundamental locus for this construction consisting of 2 points. The line through the 2 points, not through the 2 points, through any of the 2 points, they form the one secant to the fundamental locus. And the line intersecting the fundamental locus in 1 point. Those lines they form a family in P2 dual. This family is in fact 2 lines in P2 dual. And when I normalize those 2 lines, I get the 2 quadrics, the Fano variety of the quadric in P3. And this is the result, completely obvious result that we have learned in high school, that I want to explain to you, generalizes very nicely in any dimension if we are careful. So I'd like to take another example which is much more interesting. Now, the following example. And there we have to be more careful because the words become important. I consider X the complete intersection of 2 quadrics in P5, and I choose a line L, which I call delta. Okay. As I said here, if I project P5 to P3, projection with center L, that defines birational correspondence between X and P3. Okay? And now we have to describe this birational correspondence. And we have to understand what, I mean, we stop it 1 second and do a little bit of geometry. We project from the line here. If I take a point in X, so the line and the point to generate the plane, 2 things can happen. The plane intersects X in the line and the point, and that's the locus where it's an isomorphism. Or if not, they intersect X in the line and another line. So we have the line contracting. So the line contracting, they have an image here. Okay? And the image is in fact the fundamental locus in P3 is the genus 2 degree 5 curve. Now, I want to explain this genus 2 degree 5 curve, and I'm going to explain it by first coming back to the first example. How could we describe the 2 points? The best way to describe the 2 points was this, first case. So I had taken Q, in P3, and of course I'm going to take the point X to be 0, 0, 0, 1, Okay? And so since Q goes through that point, I'm going to consider dq over dx3, which is a hyperplane, and I'm going to consider q minus dq over dx3 times x3. Okay? And you see immediately that those two polynomials do not depend on x3. You see, x3 disappears here because you have the hypothesis that q goes to x. So those two polynomials do not depend on x3. You have a linear polynomial, a degree 1 polynomial, degree 2 polynomial, and they intersect into 2 points. That's a canonical way to construct the 2 points of the fundamental locus as a complete intersection of a line and a quadric. Okay? Here it's exactly the same. Here I take, so I'm going to fix L to be cut out by x0 equal x1 equal x2 equal x0 equal x1 equals 0. Okay, I choose the two quadrics, so I'm going to consider the matrix dq0 over dx0, dq0 over dx1.
You need 4 equations to cut out the line in P5.
I mean, pardon?
So this is a line in P5.
This is a line?
In P5.
You're,
Equations.
you are perfectly right. Let me repeat my. Your question is excellent because I was going to make an error. Thank you. And you knew that. You understood that. So yeah. I'm going to put L is a line in P5, so I'm going to describe P5 in this way. L is going to be defined by y0 equal y1 equal y2 equal y3 equals 0. That's L. And I'm going to separate to consider P5. Let me cheat a little bit, but I won't cheat. I'm just making an average rate choice as the P prod of C of y's and x0 and x1. Because I choose 4 hyperplanes cutting the line and 2 hyperplanes defining the line I'm choosing. I mean, good for the line I'm choosing. And I'm going to consider the matrix, the following matrix, dq0 over dx0, dy0, no, dx0, dq0 over dx1, and here I'm going to put q minus sum from 0 to 1 of dq0 over dxi xi, and here the same with dq1. That's a 2 by 3 matrix. Okay, and here this line, this is q0 and this is q1. This line, this column corresponds to q0 and this column corresponds to q1. And if I look at the maximum minors of this 2 by 3 matrix, take that the degree 2, degree 5 genus 2 curve, and this is the fundamental locus in P3. And what is easy to prove is that if I blow up the fundamental locus described by this matrix, then I get the graph of the projection under a hypothesis of generality, of course. You see? So, and my claim, and you will see later that it's easy, is that that can be generalized for any k, assuming that we have a complete intersection of quadric containing a bk. Of course, the construction, I mean, if you don't assume enough generality, you may get in trouble, but that can be very well organized. But I would like to say much more here than just that. First, let me give you an example. This here, in this case, we have those are linear terms, and we have here a quadratic rule. So here I have a 2 by 2 matrix with linear term, which determinant is a quadric. Okay? And you naturally wonder, is this quadric smooth quadric or a cone? And the two cases occur. I'd like to say this. If L is delta, if X is general, and if delta is general in X, then the quadric determinant of the dqi over dhj is smooth. And if X is, and if D not is a special line, and that has to be explained, the quadric is a cone. And if you want to know what is a special line, it's very simple. That means that there is a plane intersecting X in twice the line and nothing else. Okay. And now, so let us look at the general case. Something very interesting appears there in the general case. I'm looking at the Fano variety of X. Of lines in X. That's a variety F in G equal 5. Fa has degree 32. It's well known. The canonical lambda of Fa is trivial. More interesting and less well known, that means that you have a curve there is a curve, the special line in Fa from the virtual hyperplane section of Fa. What do I mean by virtual hyperplane section? I mean it's linearly equivalent by hyperplane. Fa is embedded in G15. That is, it's embedded in some Brucker space, and hyperplanes are made by hyperplane in the Brucker space. And I write virtual to say it means that this curve is linearly equivalent to a hyperplane section, but is not cut out by a hyperplane. See? And this is a proof which I won't give here. Now, what is interesting for me in this construction is what happens. The projection. Should I answer? The projection from P5 to P3 induces a projection that we have seen from G15 to G13. Okay, I should write this way. Of course, that can be extended to a certain blowing up of the blowing up of the cone to G15. This is the blowing up, and we have a map this way, which is a vibration in G13. And I don't want to go too much in detail. Now, my question is, what happened in this construction to Fa, which is there? Okay, and the amusing result is that, first of all, you have to understand, in order to, you have to look at the proper transform of Fa here, okay, which I will write, okay, okay, and the result, which is very easy to prove, not very easy, not difficult, because the Fa tilde is isomorphic to the normalization, the zeroness normalization of the surface of two secant line to to the genus to the fundamental locus curve, the fundamental curve. In P3. And the map can be very well described. You see, when you look at this projection, how do you describe this projection? We have started with a projection from a line. So what happened is that in the line is the point in G15. G15 has a tangent space in the Brucker space, and you project in the Brucker space from the tangent space. Okay? And in this projection, G15, the image of G15 is in G13. Okay? And in order, and as you know, the tangent space to the G15 in that point intersect G15 in the cone with vertex in the point over a second. Okay, so as you know or you don't know, as you can find it everywhere, I mean, it's not difficult to understand. So this is the blowing up of G15 along this figure, and this is going to be the blowing up of the FA along the intersection of the tangent space with the Fano variety. And it's very interesting to look at the intersection of the tangent space with this Fano variety, because this intersection has two connected components. There's one point corresponding to L, which will be a singular intersection, and then there is a curve, the so-called incidence curve, okay, which is just through which doesn't go through the point except when the line is not general. It doesn't go through two components. And since FA is the surface, blowing up the intersection with the curve, the smooth curve, you don't change anything. You only have to blow up this one component consisting of the first infinitesimal neighborhood of a point. Okay? So you blow up that, and this is in fact the blowing up of FA. So you find this isomorphism, and from this isomorphism you recover something which is very, very well known. And for example, studied in Griffiths-Harris, if I remember well, somebody told me that FA is in fact the Picard variety of that curve of degree, the fundamental locus, the curve of degree 5 and genus 2. Okay? And a good way to describe it is you can also, with this construction, very well describe the group structure of this Picard variety by using just the hyperplane section. It's very nice. So you cover all the I finish at 20 or 30? 20. So, from this you find that FA is the Picard variety of the curve of genus 2 and degree 5. And of course, you have this very interesting curve of special line in FA, and you wonder what happened to that curve of special line under that projection. And what is also very nice is that, as I told you, when I write this here, I'm speaking of the surface of 2 secant line, I'm speaking of the normalization. So you wonder what is the singular locus on the surface of 2 secant line for that curve. As we've seen, that curve is an intersection of a quadric and 2 cubics. Okay? And in fact, the singularity is on the quadric, it's a 2-3 correspondence. So there is a family of 2 secant and a family of 3 secant. Okay? So the family of 3 secant, it's a conic, as we have seen, because it's one of the family of the quadric. And this is the triple as well as the singular locus of this surface. So when you normalize, you just know the only singular part is this conic. The singular part is this conic. So everything is very clear. And what you wonder here is what happened to this family of special line in X. And this is also very interesting because the special line is going to be under that isomorphic to the curve of so-called stationary secants. What are stationary secants? Are those 2 secant lines which intersect the curve in 2 points whose tangent meet. If you take the general secant, that's the trisecant lemma, the two tangents do not meet. And there is a family of dimension 1 of bisecant whose two corresponding tangents meet. And they form a curve, which is important in the Boulot Italian geometry. And this curve there, of which we don't know much, is in fact isomorphic to the curve of special lines in the Fano variety. Okay? And as in particular, because we can describe what happens in normalization, this curve is going to be smooth because this curve is smooth. Alright, there is much more that can be said about that, but I'd like to explain what is all this about, what I want to do with all that.
Can I ask the one question? If you obtain all curves of genus 2 this way,
Pardon?
you obtain all curves of genus 2 this way.
I'm saying
All curves. All curves. You have a curve of genus 2.
yes.
Does this construction give you all possible curves of
Yes.
genus 2? Yeah. And does
Any
that-
curve of genus 2 is embedded in P3 with degree 5, and if you take a curve of genus 2 of degree 5 in P3, you blow it up and you get this.
And does this curve then determine x by to projective transformation rate?
This is what?
Does the curve,
Yeah.
abstract curve, determine x up to projective transformation?
Yes. I mean, determines the Fano variety of x. And does it determine x? I didn't think about that question, but perhaps. Good question. I don't know. No, I didn't-
Some additional structures in it.
I don't know. I mean, the variety is defined, is characterized by its Fano variety or not? Yes?
Yes, yes.
Yes. Oh, we have already two votes for. So that's the answer to your question. Okay, well this is well known, but maybe not the detail here, and also the fact that you can describe the group structure very well from that construction. It's very simple, and I don't have time to do it here, but it's nice, I like it. Now, what is the question I want to attack with this construction is this. Of course, I'm writing equations and matrices. I shouldn't. I'm writing them to hope to make this clear. Because I should write with bundle and decompose bundle and write things with decompose bundle. But I more or less thought by being a little bit explicit with quadrics and giving the equation that could help. But of course, this is not the right way to do it. So, here is my general construction. I come back to the general situation. Let's assume X is general, which implies that in order that there is a pk in X, it implies something like n minus k minus k plus 2 choose 2 must be positive. It's a simple calculation. In order that there is in X always a pk. That's just computing the dimension of the Grassmann. So I perform exactly the same construction. I consider the matrix N. Maybe I should write delta is defined by y0, y, n minus k minus 1. How many do I have? It's cut out by n minus k, so right, it's okay. And delta cut out by, and delta is going to be p of prod of c of x0 xk. And I'm going to consider, as before, the matrix M, which is here a quadratic matrix, dqi over dxj, and here a row consisting of q0 minus some of dq0 over dxj xj, and then the same with the last one here. And the same with n. Exactly as before. Okay? That is that I can recover any quadric by looking at the color. Right? And I'm going to consider S1 in P of cross of C of y0 y n minus k minus 1 cut out by the zeroth fitting ideal of n. Right? Of course, here I'm doing that in general. I should tell you that I don't have to do that. I can do that without assuming in general that I have condition under very precise conditions which are necessary and sufficient. We know that the contraction can be performed. But it's easier for this to discuss the problem to look at the general situation. So I'm considering this thing, and that's the first claim, which is not difficult to prove at all, is that the graph of the projection
Zeros fitting ideal is just degeneration locus.
Pardon?
This fitting ideal, is
Yeah.
it just the degeneration locus for the symmetries? What is
What
this?
do I mean by fitting? And it's good. The variety cut out by the maximum matrix. And I'm wrong with the notation. No, that's I have to go down. I think to make things convenient. Zeros, yeah, maximum matrix. I should write. In fact, it's very useful in this contraction to consider the SI cut out by the no, S1 is cut out by the 0, so SI is cut out, S2 is cut out by the I minus 1 fitting ideal. They play an important role. Okay, anyhow, my first claim is this, and this is easy to prove. The graph of a projection x tilde is isomorphic to the blowing up of P of Pn minus k minus 1 along S1. Okay, so those are the alike, and they are cut out by hyperplanes of Pn cross P n minus k minus 1 in Pn tilde, which is the blowing up of Pn. When you say, why do I add this last condition? Because it explains everything.
Where are they?
Pardon?
What is cut out?
What is?
Cut out. You say that it's a blowout along S1 and they are cut out?
I'm
One
not,
line, yes. Middle of the board, right board.
the graph of the projection.
Yes.
Which I write
It's
x tilde.
isomorphic to the blowout
The blow-
along S1.
The fourth line.
Fourth
Going
line,
on.
fourth word. Two words. What is cut out?
The graph.
And they are, and they are cut out.
What are
They are the same. I mean, so I understand your question. Sorry. The graph of the projection is embedded in the product of the 2D and 2 space. Okay? It's embedded there, and I claim it's cut out there
Okay, that's what it's cut
by by a bunch of linear. In fact, it's a complete intersection.
Okay, yes.
Okay. It's got on. They are the same.
So,
They are.
so the graph.
Pardon?
So you are speaking about the graph. Right? Graph is
Yeah, graph. I mean, I'm just describing the correspondence. Blowing up x along L is the same as blowing up E n minus k minus 1 along the fundamental locus S1. The two are naturally isomorphic. And it's very important because once you understand that, you know that they are cut out in the blowing up Pn tilde of Pn in L by hyperplanes. Once you know that, for example, you know that all fibers are linear spaces. And if you know that all fibers are linear space, you understand that you understand everything. There is no more work necessary. And that's why I wrote it here. Okay. Okay. So, and in this construction, you can see coming out those vectors, and they help very much to describe the incidence variety of inside the final variety of the completed section X. But I would like to state my conjecture before it's too late and explain why it should be true. So, here is my conjecture. By the way, all that is a work done by somebody called Arisa, Dan Arisa. He's a Brazilian person, so Skype has been very useful. And we are three, Arisa, Skype, and me. So here is my conjecture. So I look at FA of X, the final variety of lines in X, okay, as before. So I can erase that. Yeah, I need to be a little more formal. Let's assume that I'm going to add W is to be the vector space generated by y0, y n minus k minus 1, and V is going to be the one generated by x0, xk. Okay, and I'm going to write U to be the sum of W and V. Okay? So G15 is in P of lambda 2 of U. That's the Kluge space. That projects.
One circle.
Pardon?
G1, one circle. 1 point.
G1n, I'm sorry, thank you very much. G1n is embedded in the Kluge space P of lambda 2 of U, which projects naturally to P of lambda 2 of W. Okay, and we know that by this projection, the image I should write perhaps for the sake of simplicity, G to U use go back in notation, and G to W. Becoming French once more and going back to notation. So here we have this natural construction, and you see when we write it this way, what is this project? This is not anymore projecting from the tensor space because we have a very big space. So we project from, nevertheless, from a space which intersects Grassmann in a cone with vectors in a Grassmannian over a second variety, once more. So it's much more complicated. So here in this construction, we have the blowing up, which is easy to describe along the center of projection, and the map is well defined. This is the vibration in Grassmann variety. Here I have the final variety, and here I have the proper transform of the final variety, and here I have an image which I'm going to call Hilda. k+1 of S1 normalized, because this is my conjecture. The conjecture is that FA tilde is smooth, and is the normalization of the variety of k+1 secant 9 to S1. Okay? So let me give you an example. So, for example, it's true for k equal 2 and n equal 8, which is an interesting case. Okay. I'd like you to notice that the case k equal 2 and n equal 7 is very special because the variety cannot be, the x cannot be general because the complete intersection of 3 quadrics in P7 does not contain any plane. Okay? But still, it can be smooth. It is, in general, it is smooth. And it's very interesting because by using this computation, you prove that the final variety of such a, in this case, cannot be smooth. It cannot even be conical. This comes out of this construction. It's a useful construction. Okay, for many other applications. I'm trying to keep track on what I'm trying to say to you. Okay? So in this case, it's a long story, but it's possible to prove that theorem, and it gives a nice description. It has application in two directions, and of course there is the problem of the special line, but which is more delicate in FA of X, which is more delicate in this case. But this, in some sense, this difficult case justifies this conjecture. And now, maybe, yeah. Yesterday evening, I had dinner at 2 o'clock in the night with Fyodor. And we didn't drink enough vodka. So I didn't sleep well. And I think I conclude the first part of this conjecture. So, yeah. I think that was fruitful. But the finiteness is much more, the finiteness is completely different. You can do it with a screwdriver and things like that, but you need a formal proof. I mean, in each case, you can sort of push around, move around and find out why it's true. But it needs a formal proof that I cannot find. But this is, there is, I think, a very nice proof on that, based on that construction. Okay, so this is the conjecture I wanted to talk about. There's another question related to that. I wonder, this was asked to me by Fyodor, because when there are special cases of interest, is the case where k+1 times 3 is n+1. Is this the case? Yeah. Yes, this is the case. In that case, KFA is OF, it's trivial. It's a simple computation, no problem. Don't think there is any idea when I write that. I just compute. And even in that case, there is this question of deciding if this is the billion variety. Okay, and I don't know. This question was very particular, and I've been trying to think about it using the construction and using the description of the abelian variety in the case k equals 2 n equals 5, and I have no answer to that. And also, there is in this case there is the cases where you have a virtual hyperplanization which produce interesting geometric objects. So this is just work in progress, as we say. So I don't want to say too much about that. Okay. Yeah, a last application of this construction, a last and easier application of this construction is of enumerative geometry. You can, I give an example. Of course, there are theorems to write, but I give an example. It's an amusing example. Now, it's very, I mean, this continuous formula gives the classes of the classes of varieties parameterizing linear space let's say parameterizing PL in X intersecting delta in PL minus 1. This is, I wanted to give you a specific example, but I can't find it in my paper as usual, but it's there. So it's just to say that with this construction, you can really make a lot of enumerative geometry in the final variety of X, and you can also apply the construction in the other direction to get some information about the variety SI that I produced here. Okay, I think I will stop here because this is already, you are already away from me and me away from you, but I try to do my best to interest you in this construction.
So, any questions?
So this case of interest, then 3 times k plus 1 equals n plus 1. So I guess most of these cases are out of your genericity condition, yeah, because your genericity condition n grow through quadratic.
Yes. So to get, I mean, genericity on one side is equivalent to genericity on the other side. And to be sure, I mean, you can also look at special case and still perform the construction. But you have this, for example, you can even perform the construction when you have singularities in X, in delta. But you have to be careful that, in fact, and this is why I underline that, in order to be able to make the compute, you need the blowing up to do the blowing up. As you know, the blowing up can be approach of a symmetric algebra, approach of an algebra of part. And you need those two to be the same in order to perform the construction. And it's equivalent with the fact that the blowing up is cut off by hyperdense. It's really, this is a level of genericity you need to be able to perform the construction. And then you can count on one side with using the other side. Everything is done by that construction. It works, you know. Contrary to what I tried to explain, it's easy. I made it very good.
More questions? So in the same direction, do you have channels on N for which you can still find the smooth X?
Well, yes. The smooth, those are given by the determinative formula. You need, I mean, you need, the bounds are, when do you have, if you have delta in X, you see immediately when it's possible that X is smooth along delta. You look at the conormal map, and it has to have maximal rank everywhere. And that's necessary. If you have that condition, and that's the determinant condition, you use the dimension, I mean, the codimension of the vanishing locus. As long as the codimension is large enough, you get smoothness, and outside delta, there's no problem. So, but that doesn't define the construction. See? And it's the same. You see the atomic it comes up when you perform the construction to get the isomorphism. Very natural. It's the same question. It's amusing. It's the same question when you say you brought a subvariety. That means that's the geometric description of a block. And when you brought an ideal, you brought the symmetric product of this ideal. And that's not the same as the sum of the parts. Those are two very different drawings. And this type of condition they are taking, attacking, they appear in that construction. So there is algebra. That's what's for Hilda. Salieri is coming up.
More questions? So let's go to begin. So we meet in 8 minutes.